the first action potential in the heart takes place in the SA node. When the SA node depolarizes, before the action potential moves on to the atria, all of the atrial muscle cells are at the resting membrane potential, which means that their outer surfaces are positively charged. So, when all of the cells are at resting membrane potential and the outer surfaces are positively charged, there is no dipole in the heart. So, electrocardiography does not record anything, but it draws an isoelectric line, which is the line before the P wave. The right atrium starts to depolarize at the point close to the sinoatrial node, and the outer surfaces of the atrial muscle cells there become negatively charged. Now we have a dipole in the atria, and electrocardiography can start recording a wave. We know that the heart is three-dimensional, atria are three-dimensional, and therefore the electrical activity is spreading in many different directions. We can show these spreading directions by black arrows. And then during the spread of action potential, many dipoles form, and these are also in many directions. We can represent these dipoles by red arrows. You can see here that the tip of the black arrow represents the direction in which the electrical activity depolarization is spreading, and the tip of the red arrow is telling us the positive end of the dipole that is formed during this spread. Here, both of them are in the same direction, therefore it may look a little bit unnecessary, but when we talk about the T wave, we are going to understand, I'm going to try to explain that the direction of the spread and the direction of the dipole and their relationship is really important. Electrocardiography puts together all of these dipoles, so we can draw a single vector representing the dipoles produced during the spread of depolarization in the right atria. This vector is from right to left and upwards to downwards. Then the electrical activity spreads to the left atria. Again, left atrium is three-dimensional. There will be the electrical activity will be spreading in many directions, and there's going to be many vectors or dipoles due to this. Again, we are going to take a summation vector. In the left atrium, the summation vector for the depolarization is also from right to left and upward to downward. Electrocardiography even combines the two of them. So we talk about a depolarization vector for the atria together. This is from right to left and upwards to downwards. Now, what is the relationship of this dipole to our electrode? How will this dipole be reflected to the electrocardiography waves onto this electrode? The basic electrocardiography rule says us that if the positive end of the dipole is close to your positive electrode, you are going to get a positive recording. So we can easily see that this dipole here, P vector, the tip of it is close to our positive electrode, and therefore electrocardiography is going to record a positive P wave. The rising arm of the P wave represents the right atrium, and the falling arm of it represents the left atrium. Electrocardiography records 12 derivations, 12 leads. In most of them, P wave is going to be positive, but as we move on to new videos about electrocardiography, we are going to learn that there may be normally some negative P waves in some of the derivations, and there may be even some biphasic p waves. We are going to discuss these p waves later on. The vector of p wave under normal conditions is between 0 to 75 degrees, plus 75 degrees. When all of the atria depolarize, let's move our p vector aside. When all the atrial muscles are depolarized, the outer surfaces of all of the cells in the right and left atria are going to be negatively charged. Now there is no longer a dipole in the atria, as you see here, and therefore electrocardiography once again draws an isoelectric line. This is our PR segment. It starts at the end of P and ends at the beginning of the QRS complex. At this point, just looking at this figure, you may say there's a dipole here. There's a negative end in atria and a positive end in the ventricles. But it is not like that, because there is a fibrous tissue which acts as an insulator between the atria and the ventricles. A dipole cannot form between the atria and the ventricles, and therefore in a condition like this we have an isoelectric line in our electrocardiography recording.